We have talked about we've talked about finding rules for sequences and then series. We're back to just talking about sequences, and this is like sort of like a weird idea here. But now we're going to talk about something called an explicit rule. So an explicit rule gives a sub n as a function of the term's position number n in the sequence. So we have been using explicit rules. We've been talking about like in terms of like where things are at. You can plug in an n and solve for it, and you can find any term like that's in that spot. So if we plugged in 5, we would get the 5th term. Now we're going to talk about something called a recursive rule. Recursive rule that gives the beginning term or terms of a sequence, and then a recursive equation tells how that a sub n is related to one or more preceding terms. So now this is dependent on like what terms you have. And I think it's a little clearer once we do some examples. So let's look at example 1. In example 1, we're going to write the first 6 terms of the sequence. And what they give us is a single term in the sequence, and then they give us the recursive equation. So this is a weird part, and I think I saw probably Jacob was doing his Go formative already and was trying to do where you're given the rule. And for the rule, you do have to have a single term or maybe 2 terms and the equation. So you'll have to have both parts. And it's weird because I'll show you when we do example 2. It's weird because it's like, why do I need this? But for this first 6 terms, we know that the first term is 1. Now, to get the second term, or my a sub 1, let's look at this formula. It's a sub n equals a sub n minus 1 plus 4. What does this a sub n minus 1 mean? If you think about a sequence, what does that represent in relation to our n? Yeah, it's the one before it. It's not necessarily the last one. It's the term before this term. So you have to have some kind of, I think of these as like an anchor term or something, because that's what you're in relation to that term. So my a sub 1 would be a0 plus 4. And again, that's just applying this rule. A1, 1 before that would be a0 plus 4. Well, my a0 was 1 plus 4, which is 5. So then my a2, which I could not have found without finding my a1 first, because it's a1 plus 4, which would be 5 plus 4. And yes, it's going to be 9. So you'll see a pattern coming, but I'm going to show you all of these anyways. A3 would be my a2 plus 4, which is 9 plus 4, which is 13. My a4 would be a3 plus 4, which is 13 plus 4, which is 17. And then my a5 is a4 plus 4, which is 17 plus 4, which is 21. This only asks for this first 6 terms. So the answer that you would put into Go formative is something like 1, 5, 9, 13, 17, 21, because that's 6 terms. We probably get the idea, but I'm still going to show you example B because it leads into sort of like our rules and seeing some patterns here. So for example B, notice in example A, we had a sub 0 equals 1, and in example B, we have a sub 1 equals 1. I told you when we were doing the series that it matters, and now it doesn't. We just need a point that's kind of like centering us. So if I want my first 6 terms, I'm given a1 is 1. And now my recursive equation, which is this part, is 3 times the term before it. So a2 will be 3 times a1, which is 3 times 1, which is 3. And obviously here I'm showing you every step in your work. You wouldn't have to write all of these things. It's a bit redundant, but for our notes, it's good to have these definitions. My third term, a3, would be 3 times a2, which would be 3 times 3, which is 9. My fourth term would be 3 times a3, which is 3 times 9, which is 27. My fifth term would be 3 times a4, which is 3 times 27, which is 81. And then finally, my sixth term is 3 times 85, which is 3 times 81, which is 243. So on my homework, I would enter in 1, 3, 9, 27, 81, 243. Are there any questions just about finding these first 6 terms? Pretty straightforward. All right, now let's just look at these. What is the difference between A and B?
It's obviously arithmetic and there's geometry.
Exactly. One of them is arithmetic and one of them is geometric. And we can tell that because this one is adding numbers and this one's multiplying, right? And that gets back to our common difference versus our common ratio. So that's what this part here basically says. It says in part A of example 1, observe that the differences, or that common difference, of consecutive terms of the sequence are constant, so the sequence is arithmetic. In part B, the ratios of consecutive terms, which is our common ratio, are constant, so the sequence is geometric. So we can then use this idea to get these 2 rules here. So if you recognize that something is an arithmetic sequence, you can just apply this formula to find the common, or I'm sorry, the recursive equation. And if you recognize that something's geometric, you can just apply this recursive equation to find, or I'm sorry, to apply this rule to find the recursive equation. So it's nice we still have some equations that we can just apply. So example 1 was where I give you a term in the recursive equation. Example 2 then is when now I give you the sequence and I ask you for the recursive rule. And remember, the recursive rule is going to have 1 or more terms, and then it'll have the recursive equation. And it's sort of weird to see why in example 2, but we'll see why that might be necessary in example 3. So example 2, and this should be A, but it says C because of course. I wrote these this morning and I guess I wasn't checking myself. The first thing we need to basically see, is this arithmetic, is it geometric, or worst case scenario, is it neither? In this case, how would you go from 3 to 13? What with 10? Add 10. And then 13 to 23, I'd add 10. 23 to 33, I'd add 10. 33 to 43, I'd add 10. So is this arithmetic, geometric, or neither? It's arithmetic. And so, like, I don't need you to write that in your homework or anything, but it's good that we start kind of thinking about those things as we're doing this, because it makes our job easier if we know what we're working with. So since it's arithmetic, I know then that my recursive rule would be my first term, which is 3. And my rule would be a sub n equals a sub n minus 1 plus my common difference, which we identified as 10. Now again, just to be super, super clear, why we need the a sub 1, like I said, I think of it as an anchor. Say you didn't put that a sub 1 down, then you don't know where to start, right? And say you started at 2 randomly. 2 is not in this sequence, but sure, you could start at 2 and you generate another sequence with this recursive rule. So that's why you really have to have at least 1 point here, or 1 starting term in your sequence, so you know where to start, because otherwise there's unique sequences based on where you're starting. All right, let's look at part D, which really should be part B. How would you go from 16 to 40? This one's trickier. I heard it.
2.5.
Yeah, what are you doing with that 2.5? Multiplying. So this is times, and I'm going to put it as a fraction, 5 over 2. If you're not sure, if you couldn't have recognized that easily, which I didn't, honestly, yeah, that's 2.5.
Oh,
2.5. So 40, what you would just do is you take one term divided by the term before it, because that's a common ratio, and you get 2.5. If you're not sure what that is as a fraction, you hit math, fraction, and hit enter, and you get 5 over 2. And again, 40 times 5 over 2 gets you to 100. 100 times 5 over 2 gets you to 250. 250 times 5 over 2 gets you to 625. So is this arithmetic, geometric, or neither? Geometric. It's multiplied by a common ratio. So now I'm going to apply that rule. Again, I need my anchor sort of part. So I'm going to say A1 equals 16. And then my equation would be A sub n equals 5 over 2 times AN minus 1, the term before it. Any questions about applying these recursive equations given a sequence? Okay, so example 3 now is writing recursive rules for special sequences. So this is where we're going to have something that's neither arithmetic or geometric. And this also sort of gets into why recursive rules can be helpful. It's not the only reason, but I was thinking as I was making these notes today, like, who cares? We already have a perfectly good way to generate sequences. Why do we need another way? Well, recursive rules are good for sequences that would be difficult to write as an explicit rule. So these would be difficult to write as an explicit rule. And that's what we were doing before. But if you look at part A and B of example 3, you're going to see there's some issue with just like writing an explicit rule for this. So example A is 1, 1, 2, 3, 5, ... Does anyone recognize what that is? If I have any like just math geeks in here.
Isn't it Fibonacci?
Yes, it's Fibonacci sequence. Yeah, so you, even if you're not familiar with that term, you might actually know it. If you've ever seen the golden ratio or that golden spiral, you'll see it like over conch shells. That is Fibonacci sequence. The idea of Fibonacci sequence is that you take the terms and you add the two terms before it and you get to the next one. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5, our next term would be 8. And then it'd be 5 plus 8, our next term would be 13 after that. So that's what Fibonacci sequence is. So just to put that into words, beginning with the third term. I guess I can abbreviate here. The third term. Each term is the sum of the two previous terms. So now we have to begin with the third term because we cannot assume that the term before this is 0. We're starting at 1. So this is a weird one where we actually need to name two terms. And again, that's because it's the sum of two previous terms. So I need to state that my A1 is 1, but also that my A2 is 1. So these are going to be ones where you have to actually state two terms in your sequence. Because again, if we started at a different A1 and 2, you could still apply this rule and have a totally different set of numbers. And then my rule or my equation here would be A sub n equals, and you can either, the book does it A sub n minus 2, which means 2 previous, plus A sub n minus 1, which means 1 previous. You could also put A sub n minus 1 plus A sub n minus 2 because addition is commutative and the order doesn't matter here. Any questions about that one? Interesting. Part B almost looks like that. I don't know if this has a fancy name, this one. I would imagine it does. I'm just not sure what it is. So basically what you can do for this one is let's denote the first term by A sub 0 equals 1. And if we do that, let's notice that A1, which is 1, is equal to 1 times A0. Likewise, A2, which we see as 2, is equal to 2 times A1. A3 is equal to 6, which we could rewrite as 3 times A2, and so on. So basically, instead of in this pattern we were adding, this pattern we're multiplying. So you can see that these two previous things would be 1. No, this one. 1 times 1 is 1. And then you have 2, which is 2 times, and we're increasing this number here. And this is like our space. So that's why we had to start at A0, because our first term is equal to 1 times A0. So that's where the shift comes in, because this is increasing every time. And so our rule or our equation, again, we need to name some terms. Here we only have to name the first term. And then our A sub n is n times A sub n minus 1. So now that I've written this down, let me re-explain that. We started at A sub 0, so that this first term would be, we want this to be 1 when we first apply it. Does that make sense? I'm not saying it's great. So in order to make this work, your A sub 0 is not really like applied with this rule, because otherwise it'd be 0 times that. So that's why you're starting here. And so the second term, our second one, is where we're really applying this rule. And that's why this needs to be the 0 space, the first space, the second, the third, the fourth, and so on. Okay, those are probably our hardest ones. I have one on your homework that looks like that. I made another mistake. I forgot to give you a definition. So draw a line. The last part, if you notice our learning objectives, we had some weird words. We had the word recursive, which we've not seen in math before. We also had the word iteration, and I need to define that for you. So iteration involves the repeated composition of a function f with itself. So iteration involves the repeated composition of a function f with itself. So way back in chapter 3, before I was ever here, you all did function composition. That was the f of g of x or whatever, or g of h of x. Iteration allows us to do that as well. So basically the result of one iteration is f of x. 2 iterations would be f of x. Do I have enough parentheses there? Yeah, and so on. Okay, so the result of one iteration is f of x. 2 would be f of x, and so on. Okay, so that sounds all quite scary. It's quite straightforward. So how you actually do this, we can just flip. I don't normally make you write all that stuff, sorry. So how you actually do this, and I only gave you one example because it's that straightforward. In example 4, we're going to iterate a function. So we're going to find the first 3 iterates, x1, x2, and x3, of the function f of x equals negative 3x plus 1 for an initial value of x0 equals 2. So our first term here, we're going to do, our x1 is going to be f of x sub 0, which they told us was 2. So it's going to be f of 2. I don't need to color code, but I'm going to. F of 2, which is equal to negative 3 times 2 plus 1. And that's going to give us negative 5. That's our x1. Our x2 is then going to be f of x1. Well, we just found x1. x1 is going to be f of negative 5. Or sorry, x2 is going to be f of negative 5, which would be negative 3 times negative 5 plus 1. That's positive 15 plus 1 is 16. Then our third term, x3, is going to be f of x2. So x3 is going to be f of 16, which is equal to -3 times 16 plus 1, which gives us -48 plus 1 is -47. Oops, I'm off the page. Also, I forgot to do it in pink. It's -47. So on Go Formative, all you do to enter these answers is you just have a list, -5, 16, -47. So iterations are a kind of cool little application of these recursive sequences.